Okay, let's go ahead and get started. Let me just start with a couple of administrative announcements. First of all, problem set 3 is here for you to pick up. So if you haven't gotten it already, make sure to grab it on your way out of class. Second, just a reminder, problem sets are due at the beginning of class, not in the middle of class, at the end of the class. Thank you for your understanding on that. I appreciate that everyone turned in their problem sets at the beginning of class today. Just also, let me check. Did everyone get my email? I sent out some announcement a day or two ago. If you didn't get the email that I sent, that means that you should let me know. Okay, because it means that something somewhere is going wrong with the universe. Okay, today I would like to continue with our discussion of the geometry of space and time. So, last class, we began to understand why it was correct to use the word geometry when we talk about the structure of space and time. And in particular, we saw that just as in Euclidean geometry, the length between two points, or the distance between 2 points, given by the formula L squared is delta x squared plus delta y squared, is independent of the choice of coordinate system. In special relativity, we saw that there's an analogous quantity that one can define. So if we have two events which take place at a spatial separation delta x and a time separation delta t in some particular coordinate system, then the invariant interval delta s, given by the formula delta x squared minus c squared delta t squared is equal to delta s squared, is independent of the coordinate system, or in other words, independent of the choice of observer. So to state this slightly differently, just like in plain Euclidean geometry, the values of delta x and delta y between 2 points can depend on the orientation that you choose for your coordinate system. In special relativity, the time separation delta t and spatial separation delta x between two events will depend on the observer who's doing the measurement, i.e. will depend on the choice of reference frame. But nevertheless, this particular combination, delta x squared minus c squared delta t squared, does not depend on the choice of observer. That means that it is physical. One of the basic principles of physics is that the outcome of some physics experiment should not depend on the choice of coordinates that one uses to parameterize the various dynamical variables that describe that experiment. The period of a pendulum shouldn't depend on whether I choose to describe the position of the pendulum in terms of the angle that the pendulum makes with vertical, or in terms of the vertical position of the end of the pendulum, or the horizontal position of the end of the pendulum. The different choice of coordinates that I use to describe a system shouldn't change the actual physics at the end of the day. And so what we have identified here is a combination of coordinates, delta x squared minus c squared delta t squared, which is independent of the choice of observer, i.e. independent of the choice of coordinate system. So this should be a very important physical quantity. And we began last time, and will continue this time, with understanding exactly what the meaning of this quantity, delta s, is. So first of all, we saw that, first of all, this quantity, delta s squared, can be either positive or negative, meaning that delta s can be either real or imaginary. And we saw, first of all, that if delta s is equal to 0 for two events, then that means that delta x is plus or minus c delta t. And the two events can be connected via light ray. In which case we say that those two events are either light-like separated or null separated. Likewise, we saw that if delta s squared was less than 0, so that delta s is purely imaginary, then there is a frame in which the two events happen at the same place, so that delta x prime would be equal to 0 in that frame, but at different times. So that delta t prime is not equal to 0. And then, in that case, delta s is related to the time between the events as measured in the frame where they take place at the same location. So in particular, delta s squared is minus c squared times delta tau squared, where delta tau is the time separation in the frame where the two events take place at the same location, which is to say it is the time between events in the frame where they are at rest. And this has a name. We call this the proper time between the events. So whenever you talk about a time interval in a frame where the objects being studied are at rest, you're really talking about a proper time. And although the delta t between two events can depend on the frame in which it is measured, the proper time between two events does not depend on the frame in which it is measured. If I have two events that are happening here, and I want to measure them in my frame, where the events might be moving, and I say, what is the time between the events in the frame at which they are at rest? What is the time between the two events in the frame in which they are at rest? Then the answer that I will get is the same as the answer that you would get if you asked yourself, what is the time between these two events in the frame in which they are at rest? So hopefully that's clear. So, in this case, we say that the events are time-like separated. Any questions on this? So this is where we left off last class. And so let me now consider the third case, where delta s squared, which was delta x squared minus c squared delta t squared, is greater than 0. And in this case, delta s is real. And in fact, it's easy enough to see, as we will show in a minute, that this means that there exists a frame in which the events are simultaneous. That is to say, delta t prime is equal to 0 in that frame, but the separation between the two events, delta x prime in that frame, will be non-zero. Okay, so let's see why it's possible to set delta t prime equal to 0. Well, if you start out with delta s as measured in some frame, in terms of delta x and delta t in that frame, then in a new frame, S prime, the time separation delta t prime is just given by the Lorentz Transformation law. So it's delta t minus v over c squared delta x is equal to 0 if the velocity with respect to which that the primed frame is moving with respect to the unprimed frame is given by the solution of this equation, so that v is c squared delta t over delta x. Okay? But remember that delta s squared is positive. So we can divide delta s squared by delta x squared, which is also positive, to get 1 minus c squared delta t over delta x squared, which is going to be positive, which implies that delta t over delta x has an absolute value that is less than 1 over the speed of light, so that comparing that to our formula for v, the absolute value of v is less than the speed of light. And this is indeed a demonstration that it's possible to choose a frame S prime, which is moving with some velocity less than the speed of light with respect to our original frame S, in terms of which the two events happen simultaneously. And then in this frame, delta S is just delta x prime. And what is the physical interpretation of it? It is the distance between the events in the frame where they are simultaneous. Less than c. Did I make a mistake here? No, I don't think I made a mistake. Everyone with me on this? Okay, good.
It's less than c, it would be at the same place, right?
No, v is the relative velocity of the frame S, which is the original one where I've measured delta x and delta t, and the frame S prime, which is the one where the two events will take place simultaneously. And so one of the things, which as we will discuss in great detail later on in this course, all observers will need to travel at speeds less than the speed of light. I haven't actually explained to you why that is. That will come in when we discuss energy and stuff like that. But implicit in a lot of what I've discussed is that we're discussing speeds less than the speed of light. For example, the gamma factor, 1 over the square root of 1 minus v squared over c squared, only makes sense if v is less than c. Otherwise, it's imaginary and stuff like that. And, stuff gets weird. And we'll explain exactly how it gets weird later on this class. Good. Yes?
Yeah, is that absolute value v at delta x over at delta t? Is that what?
I'm just plugging in this formula here. I'm sorry, maybe that was your, yeah. No, sorry, maybe that was your confusion. I'm just plugging in that formula over there. Yeah, it's the inverse of the usual relation. Good. No, that's an important point, actually. Thank you. So, in this case, there's a special language that we use. So, if delta s squared is positive, we say that the events are space-like separated. And we give a name to delta s. Delta s is the proper distance between the two events. Which is to say, it's the distance between the two events as measured in the frame where they take place simultaneously. So, in fact, What we have seen here is that in special relativity, it is impossible to assign both a distance between two events and a time separation between two events. However, you can assign either a proper distance between the two events or a proper time between the two events, depending on whether they are space-like or time-like separated. So you can't have your cake and eat it too. You can't get both a distance and a time between two events, but you can get one or the other depending on the kind of separation between those two events. And in fact, this begins to make clear, at least, how we should think about causality in special relativity. So this is the subject that I'll turn to now, but first let me see if there are any questions. Yes?
I don't get why we couldn't have like two events separated by distance and time at the same time. Is that what you're saying?
Yes. Yes, you can have two events separated by delta x and a delta t, but the values of delta x and delta t depend on the observer who is making the measurement. Okay. So if I ask, what is an observer-independent quantity associated with that pair of events, you can either have the proper distance between the two events, delta s squared is positive, or the proper time between the two events, but not both. Hopefully that. Thank you for the question. Yes?
About that, like before that, is the delta T over delta X is epsilon over C?
Yes.
Then shouldn't delta X over delta T be?
No. Yeah. So the V that I'm using here is this V. Okay. So usually you're used to seeing expressions like delta X over delta T being equal to V. So as you can see, if you just try and solve this equation and set it equal to 0, V will have to be delta T over delta X. But it'll have to have a factor of C squared, okay, in order to make the dimensions work out. If it would make you happier, I could rewrite that equation as delta X over delta T times V is equal to C squared. And so I could call delta X over delta T one velocity, some other velocity. Okay. If that would make you happier, you could look at the equation that way. If this derivation is not clear, well, go through it again, because you should have worked it out on the problem set you just turned in. Okay. You may have worked it out correctly, but using a somewhat different language. Okay. Because you hadn't learned the language of invariant intervals at this point. But it is, morally speaking, the calculation that was asked of you for one of the problems on the problem set. Okay. So maybe I can continue, and hopefully some of your questions will be made somewhat more clear. So in order to think about the proper distances, proper times, and such a little bit more clearly, it is convenient often to draw events on what I will refer to as a spacetime diagram. What is a spacetime diagram? It's a diagram where I draw events as points and where the different axes refer to space and time, respectively. So, for example, I could have a time direction running vertically, which is the standard convention on space-time diagrams, and a spatial direction running horizontally. And in order to draw my diagrams in two dimensions, I will only consider one spatial direction. And in particular, the sort of space-time diagram that it is very useful to think about is the sort of space-time diagram where the vertical axis is not t, but is c times t. And the horizontal axis is x. So instead of plotting the x and t coordinates of some event, I could plot x and c times the t coordinate of the event. It's a free country, at least last time I checked, and so I can do that if I want to. Now, why is that an intelligent thing to do? Well, with this choice, light rays will travel on 45-degree lines. So, for example, if you have one event at the origin, then the light rays that will connect with that event, let's say that event is me turning on a light bulb, then the light rays will travel out along these 45-degree lines. And the second feature of this diagram is that objects traveling with velocities that are less than the speed of light will move on lines more vertical than 45 degrees. Okay, if you think about it, that should be reasonably clear. If an object is sitting still, then that means that its x-coordinate is not changing, so it's traveling on a completely vertical line. If an object is moving at the speed of light, it's traveling on a 45-degree line. So if an object is traveling at a velocity between 0 and the speed of light, it'll travel on some line that's more vertical than 45 degrees. Question?
Doesn't that mean that the space between the 45-degree lines and the x-axis are effectively wasted?
No. Okay. No. So, excellent question. Okay. So, what then is the interpretation of these various regions? So we see that given one event, which I've chosen to take place at the origin, you could look at another event and plot it on this space-time diagram. And you could ask, what does it mean when it is either inside or outside of those vertical lines that intersect the origin at 45 degrees? Well, the first thing that you should notice is that if your other event lies on one of those 45-degree lines, then those two events are connected by a light ray. So they are null separated. And you can actually convince yourself just by staring at the formula for delta S squared as delta x squared minus c squared, or I'll write it c delta t quantity squared, that the lines of constant s, delta s on this diagram are hyperbolas. And in particular, if delta s squared is negative, that means that c delta t is bigger than delta x. And so that means that you are either in this quadrant above, between the two future pointing light rays, or in this lower quadrant down here. So if we have one event at the origin, and the other event is time-like separated from this first event, then it must lie either in that positive quadrant or the lower quadrant that I have labeled with time-like. Whereas conversely, if delta s squared, that was delta s squared negative, if delta s squared is positive, delta x is bigger than c times delta t, and you live out on the far left or the far right of this diagram. So it's not so much that we're wasting the regions on either side of this diagram. It's just they will be the positions of events which are space-like separated from an event at the origin. Is this picture clear? The picture's getting a little cluttered because I've drawn the vertical and horizontal axis as well as those 45-degree lines, but hopefully that's clear. Okay. So, yes?
Can you depict on this diagram what it looks like when delta s squared is negative?
Delta s squared is negative? Okay. Let me redraw this diagram. without using the coordinate axes. So if you have one event here at the origin, then points with delta S squared negative are time-like separated, and they live in one of those two quadrants. And points with delta S squared positive live in one of the quadrants, either on the left or the right. And points with delta S equal to 0 live at the boundaries between these two regions. Good question. Any other questions? Yes.
So is time imaginary?
We'll get to that.
Okay.
Any other questions? So, yes.
Is there a difference between the uppermost and lowermost?
Yes, that is what I'm going to be discussing now. Okay. So, there's another name that we give to points that are space-like separated. We also say that two events with delta S squared greater than 0 are causally separated. What do I mean by that? What I mean is that it is impossible to get from one to another without going faster than the speed of light. So, for example, if you took one event being the origin and another event being one far, far off to the left on this diagram, then in order to get between those two events, you would have to connect them with a line that is more horizontal than this 45-degree line representing light, which is another way of saying that you would need to go faster than the speed of light in order to get from one event to another. And traveling faster than the speed of light is bad. Why is it bad? Traveling faster than the speed of light is the same as going backwards in time. Why is that? Well, we saw that if two events are space-like separated, then there's a frame in which they're exactly simultaneous. But if you remember from our discussion of the relativity of simultaneity, if you have two events that are precisely simultaneous to some observer, then to another observer who's moving at a different velocity with respect to that observer who sees them to be simultaneous, those events could be in either order. Okay. One could happen before the other from one observer's point of view, or the order could take place in the opposite order from another observer's point of view. So, if you can travel faster than the speed of light from one observer's point of view, then that is the same as saying that you can go backwards in time from another observer's point of view. In special relativity, going faster than the speed of light is the same as going backwards in time. And going backwards in time is not a good thing to be allowed in theories of physics. In particular, if I can go faster than the speed of light, I can go backwards in time. I could go kill my grandmother. I don't want to do that. She was very nice. But I could, in principle, which would lead to all sorts of paradoxes. And these sorts of paradoxes will wreak havoc on any theory of physics that you try and construct. So it is very important that your theory of physics not allow anything to travel faster than the speed of light. And in particular, it implies that these two events cannot, even in principle, influence one another. Because if they could, that would involve sending a signal faster than the speed of light, which would be the same as sending a signal backwards in time, which means I could send a telegraph to a hitman in 1930 and ask him to kill my grandmother, which is just as bad, frankly. So, in particular, for two events which are causally separated, i.e. spatially separated, there is simply no notion of which happened first. So there is no notion of causal order, i.e. of which event preceded the other. You know, when we think about classical physics, we like to think of events happening in causal order and of our job as physicists as to write down the laws which allow us to predict the outcome of some later event in terms of some earlier event. But that is no longer our job as physicists. So in special relativity, there is simply no notion of whether two events which are causally separated take place in a particular order. Of course, that is not the end of the story, because we all still have jobs as physicists to do. But our job as physicists, now that we live in a relativistic universe, is to only discuss the causal relationship between events which are time-like separated. So events with delta S squared less than 0 are in causal contact. In particular, it is possible for one to influence the other. And more precisely, one event will be in the future of the other for all observers. So, in particular, in terms of the space-time diagram that I drew above, if I have one event that's taking place at the origin, where those two light rays cross, then the events in that quadrant up at the top are in that observer's future, and it is possible for an event which takes place at the origin where those two light rays cross to influence events in its future, whereas that lower quadrant is the past of that event, and it's possible for events that take place in that lower quadrant to influence the event that takes place at the intersection between those two light rays. So we even sometimes give fancy names to those quadrants. We call this the future light cone and the past light cone. Or we say that the points in that quadrant are inside the future light cone. Light, because light defines that pair of 45-degree lines, and cone, because if you were to try and draw this in more dimensions, I would have to draw this picture in 3 dimensions, and it would look something like that. So this would be, let's see if I can draw it. The future and past light cone, and out here would be space-like separated. So this is in more dimensions. So here I'm sketching a picture where my vertical axis is still c times time, but my horizontal axes are now the horizontal plane here, which would describe an x and a y position of events. Question?
But for events in time-like separation, will it still be simultaneous in some way?
No. Unless they take place at the same time and the same position. Okay. in which case delta t and delta x is 0. So you could say that they're null separated, or you could say that they're time-like separated. But two events that are for where delta s squared is negative, if it's strictly negative, so really less than 0, then they're never going to be simultaneous. Yes?
Okay, if you have two events in the space-like separation region,
Yes.
like you could still draw like a line that is a secret than the null line.
Yes. Yes, indeed. So what do I mean when I draw these lines? Okay. So if you have one event here, so if you choose one event here, and you want to figure out what other events are space-like separated with that event at the origin, then it's the ones in that outside the light cone far left or far right of this diagram. But still, you could consider one event here and another event up here. They're allowed to influence each other. They're, like for example, if this is the point 0, 0 in some coordinates, and this is x1, t1, and this is x2, t2, then the origin is going to be space-like separated to both point 1 and point 2, but point 1 and point 2 will be time-like separated to one another. It's possible for them to influence one another. They just can't influence or be influenced by the event happening at the origin. Okay. Fun stuff. Any other questions? Yes?
So if you had an event in the future with reference to your point,
Yes.
to a point there, and then connected that to your origin,
Yes.
are you saying that if you drew a line between that,
Yeah.
that would be an imaginary?
No, I'm saying, I haven't used imaginary time yet. I will. Don't worry, we'll get to imaginary time. No, what I'm saying at this point is that if you have one event, say up here, and an event down here, the statement that they're time-like separated is the statement that the line connecting them is more vertical than 45 degrees. Okay, in that case, I drew a line that was a lot more vertical than 45 degrees. But, for example, you could consider this line here. It's still more vertical than 45 degrees, but it's getting dangerously close. That would describe two events that, from the point of view of this reference frame, for these x and t coordinates, are related by someone who's moving at a velocity that's pretty close to light, although not quite the speed of light. Yes?
If delta s is exactly equal to 0,
yes.
What can you say about the causal relationship?
In physics, objects are allowed to travel at the speed of light. Certain special objects like photons, gravitons, and so forth. So they still can influence one another. But this light cone, this boundary of 45-degree lines, is the exact boundary of where objects are allowed to influence one another. And when we discuss kinematics in special relativity, energy and momentum, we'll understand what is special about those objects that can travel precisely at the speed of light. Good questions. This is an important enough point that I think I'm willing to entertain many questions. Okay. Yeah.
Can we use that kind of diagram to solve equations? Like you could have multiple like lines that cross at some place, and then you could like use it to solve something. I mean, what's the use of that if not like to visualize?
Well, let me. Okay, what I'm going to do is describe in more detail the geometry of this picture, and then I think hopefully it'll become clear what its uses are. Okay. Yes.
If there are two events with respect to the origin in the future light cone and past light cone, how can they?
Yes, good question. So, if you have one event which is in the future of this guy of this event at the origin, and another event which is in the past, then you can always show that one event, if you have, let's call these events A, B, and C. So if A is in the future of B, and B is in the future of C, then that implies that A is in the future of C. You know, if you want to describe laws of physics in terms of causality, where you talk about one event causing another, then you should be able to think of some intermediate event, some intermediate, you know, the fact if A influences B and B can influence C, then A should be able to influence C. And indeed, hopefully you can convince yourself from this picture that A and C are also connected by a line that is more vertical than 45 degrees. So, I mean, the fact that causality has this, I guess you would call it an associative property, is one of the sort of basic principles that allows us to formulate laws of physics in special relativity. Okay? Even though we don't have some absolute notion of space and time independently, because we have this basic notion of causality, we can still write down laws of physics that make sense. Questions?
I can prove it by saying that P is so are you free to divide into from more and then?
Absolutely. Yeah. Okay, then, okay, you could also, right, I mean, this is a good point. So let's say I have one event here. Then you could draw the light cone associated with that event. What is that light cone? That light cone is just a set of lines we draw to help remind us which events are in the past and the future of our event. Let's call that event A. You could have some other event B, and you could draw the light cone associated with B. Okay, there it is. And you'll see, for example, that both the past and the future light cones intersect. Okay. So there are some events which are in the past of both A and B, and some events which are in the future of both A and B, and a lot of events which are in the future of one but not the other, and also some events that are neither in the future nor the past of both A and B. So, for example, the points in here are space-like separated to both A and B. Question?
Are the two space-like separation codes the same?
Two space-like separation cones?
Or quadrants?
No. I mean, when I talk about points space-like separated from A, I mean all those points on the left quadrant of A and the right quadrant of A with respect to those 45-degree lines that go through the event A.
Because they're not different like future and past are for the other ones.
Oh, well, let's put it this. I understand what you're saying. Okay. On a, on the diagram that I've written here, drawn here, they look different. One of them is left and the other is right. Okay. But if you're thinking about events that take place in more than one spatial direction, and it's usually a good idea to do that because we live in more than one spatial dimension, then there's no real notion of absolute left and absolute right. Okay. Because really the picture is hard to draw, but it should be something like a cone like this. Okay. And one could also, if I wanted to try and draw a picture, I could have my event A and my event B, and I could draw the cones associated with them, and they would intersect along some parabolas that I can't really draw. Okay. And as promised, that picture is not terribly clear, but this is what you would have to draw if you wanted to work out the causal relationship between events with respect to both A and B in two spatial dimensions. Now try drawing it in 3 and your head's going to explode. Okay. Any other questions? Okay. Let me then continue. So these space-time diagrams are very useful for a variety of purposes. And one of the nice things about these diagrams is that Lorentz boosts and Lorentz transformations have a very simple interpretation in terms of this diagram. So let's try and understand that. So let's imagine that we have an event which takes place at x equals 0 and at time t equals 0. So the events which are null separated from the origin lie along these 45-degree lines. And events that are time-lapse separated from the origin lie in the future light cone or the past light cone. So let's then ask, if let's say that I have an event which takes place at x equals 0 and t greater than 0. Say that point that I've drawn on the vertical axis of this diagram. What if I did a Lorentz boost, a Lorentz transformation? How would the values of the coordinates c and t change? Well, what do you know about a Lorentz transformation? You know that a Lorentz transformation preserves the invariant interval delta s squared. And so that means that this point, if you do a Lorentz transformation, then the new c and t coordinates will be related to the old c and t coordinates in some way, but you know that the invariant interval delta s squared must be the same, so that the new coordinates of the point must lie on a line of constant delta s squared. That's supposed to be a hyperbola. It's not a very good hyperbola. It looks a little wonky. Let me try and redraw it. So there, it's okay. I.e., it's a solution of the equation delta x squared minus c squared delta t squared. X squared minus c squared t squared is equal to a constant. That's the equation for a hyperbola, just like the equation for x squared plus y squared equals constant is a circle. So, as you consider different observers and how they would measure the time and spatial separations between the two events, you should remember that these observers will see spatial and time separations with different values of delta x and delta t, but it will always lie along this hyperboloid. Hyperbola. Hyperboloid is in higher dimensions. We'll get there. And likewise, if you have an event happening at t equals 0, but x not equal to 0, those two events at the origin and at x not equal to 0 are space-like separated. And so if you ask how the coordinates x and t change as you perform a Lorentz transformation, again, the new values of x and t will lie on some line of constant delta s squared, which again is a hyperbola. And these hyperbola how do you hyperbolas or hyperbolae? Asymptote to the 45-degree lines, the 45-degree null lines. What does that mean? That means that if you imagine considering two events that are space-like separated, and you look at a frame where they take place at simultaneously, then in some other frame that's moving at a very big velocity with respect to that original frame, those two events will be very, very close to null separated, but they'll be way up here, where they're close to null separated, but not quite null separated. They're a little too space-like to be null separated. Likewise, if you have two events that are time-like separated, and let's say they take place at the same position, but different times in some frame, then you go to another frame which is moving at a velocity very close to the speed of light compared to your original frame. Then from the point of view of that observer, those two events are going to be very, very close to null separated, but not quite null separated. They'll be a little too time-like to be null separated. And you get to this null light cone, these 45-degree lines, only if you take some sort of formal limit where the velocity approaches the speed of light. Let me stop here and just see if there are any questions. Yes?
We actually went all around like doing that thing like cones and all. Can something go from the null lines to the future light cone or the past light cone?
Sure. if I understand your question correctly, I'm not sure if I do, but you could imagine that you have an observer or an event, take, say, event A, and you have some other event B, which is lying exactly on the future light cone. So it's possible to send a light ray from A to B. Then person B could send a signal up here to some person C, to some event C. And so it's possible for A to influence B and for B to influence C. So that also for events that are null separated, we also have a notion of causal order, and we have a notion of causality. So that A can influence B and B can influence C, but C can't influence B and B can't influence A. Because one happens in the future of the other. It's only for events outside the light cone that you have no notion of causal order between them. Yes?
But by changing the reference frame to be able to move it along that.
Exactly. So if you look at what the Lorentz transformations do, the Lorentz transformations always preserve these null light cones. Okay. Why is that? It's because in special relativity, the speed of light is constant in all reference frames. And if you look at that formula of the Lorentz transformation, in fact, this is how we derived the Lorentz transformation. We derived it by demanding that if x is CT, then x prime is CT prime. Okay. That's precisely the statement that Lorentz transformations don't touch these null lines. They don't touch these 45-degree lines. Okay, we're going to continue with our discussion of the geometry of space-time next class. Actually, let me take a brief poll. How many of you are familiar with hyperbolic functions? If I say the words cosh, sinh, tanh, do those make you happy or unhappy?
Or like how familiar is it?
Maybe, how many people would appreciate a 15-minute primer on hyperbolic functions? Okay, that was what I thought. Okay, so we'll do some of that next time.